Hi, I'm Stefania Soldini and I'm based at the University of Liverpool. I'm PI of origami solar cell technology for next generation of self-reconfigurable CubeSats. This is my team, Oxford Space System, Japan Space Agency, and collaborators with Glasgow. So we have imagined a inspired approach towards space exploration. So for instance, imagine a colony that can explore, coordinate, and configure. Now imagine this approach towards space exploration. The biggest challenge for the space industry is how to make space mission adaptable and reliable. So for instance, the first time um, microsatellites have been used in deep space has been in 2018. So the idea is to push the advantage of microsatellite further and have a B-inspired swarm of self-reconfigurable small satellites. So in this project, we have analyzed only one unit, but the idea would be having many of those objects of origami robotics CubeSats that can work together and then enables new mission scenario that hasn't been achieved yet. So origami are well used in space. For instance, if you think about solar panel, that's how we fold and unfold solar panel on satellite. And the reason for why we do this is because at a launch we need to have a structure that is compact in a very small volume. And this is why most of the devices like antennas has to be folded in. So origami robotics is actually very important for space mission design, especially when we talk about large deployable structures. Now, the idea we had, which is completely innovative, no one has explored before, is about using some principle of deployable structure that are solar cells. This has been quite recent use of solar cells has been tested only in 2010, and they have been used because they are kind of lightweight, very large space structure, highly reflective. So by using the optical properties of this membrane of the cell, that's what is allow you to propulse yourself, have a propulsion, free propulsion system. So there is no need of fuel, and this is just because we are reflecting the sun radiation. Now, this is an interesting problem for propulsion, but the idea I had was to consider, okay, why not using this idea for a new kind of design of satellite or origami satellite. So for next generation of solar cell, which I call a multi-operational through shape reconfiguration using the solar cell radiation. So if this you look at the traditional solar cell, the idea is to have, for instance, if you look at this new origami robot, which is being 3D printed, is to use additive manufacturing for rapid prototyping. And what we wanted to do is try to understand how we could have a fully integrated system where the cell membrane is embedded with the facet of the folding. So the idea is that each of these facets will have a different SRP, solar radiation pressure force acting on it. And this displacement in forces changing optical property will allow to achieve this folding like here. This is the challenge, and this has been a proof of concept. We firstly imagined to do this exclusively with solar radiation pressure, but as we gone through the project, we also realized that actually we could have take advantage of a combination of factors. So imagine you have something in the launcher which is in slow configuration. Now we deploy this surface, and for us, it's going to act as a solar cell. So you can imagine we want to go to Mars. So this is deployed and it acts as a solar cell and we go to Mars. Now, the second thing we can do is reconfigure this shape and, for instance, get into a shape of a pyramid, which is typically a shape of a re-entry vehicle. And now, once we have this shape, we can imagine we can re-enter on the surface of Mars. This is like the broad idea behind this project. Now, what we realized thanks to this proof of concept is that we could use a different combination of factors, not only SRP, which we have done numerical study that demonstrate that SRP in fact can allow us to fold and unfold, reconfigure the shape, but also using shape memory polymer or 4D printing. So our sail is not only using optical property now, but it also use thermal property, for instance, the heat to change the shape. So this is a case in which we use, for instance, when we are in the launcher, we deploy using 4D material, activating the 4D material, and then when we want to, for instance, change shape and reconfigure on a different shape, like for instance a pyramid or something like that, all we do, each panel will have a different solar addition pressure effect. So this is we're looking into optical control of the spacecraft effectivity. Now, this is kind of what we have in mind. And so from one idea is also that thanks to our using those optical property and 4D material, we can actually do the reverse process, which is usually not the case for deployable structure in space. They usually are one-shot devices, they are deployed and they cannot re, um, um, re, um, reconfigure on a different way. So they usually, once they're deployed, they stay like that. This is the final proof of concept in which we have used the 4D material. So this is a CAD example. So you have to imagine underneath we have the substrate of carbon, which is the material that reflects the solar radiation pressure. And in blue, this is where we have the 4D material. So what is exciting is the final result. So the final result is that, as you can see here, is what we've done with the 3D printer. So underneath, as you can see in the video, the back is actually Kapton, the front is aluminized. We need aluminized material because that's allowed to actually reflect. So what you could imagine is in this facet, we are gonna in the future, what we're going to integrate in here is hosting the optical device control, so actuators that can actually change each facet, for instance, from a nearly reflective surface to, for instance, an opaque surface. So having this force imbalance will help to configure and change shape. Now, what we're using here is an external heat source in a way that when we preheated and we have applied the force, we have this sail which is packed like in the launcher. In this case, we are heating up and it's getting flat down. Now, this is just a proof of concept. The idea will be to have some electronic embedded in this. For instance, along here, probably some wiring to activate the temperature we need for this. The material we use are not all fully tested for space. For instance, in the case of the PLA. But in any case, this is just a proof of concept of what you can achieve with the 4D material. And we have done numerical studies, which I'm not presenting today, but what we have done in our numerical study is checking how the effect of solar radiation pressure will enable this folding. Thanks to the experiment, we could understand how stiff is the folding. So, and in the end, we experimented with two patterns. As you can see, you only see the final one we've chosen, which is what we call similar to cartilage pattern because it's quite soft. We also tried with hinges, but we think this is the most efficient way and lighter way for space applications to use this soft material. So this has been a quite exciting project. And the next step would be to use space material to explore more origami design and see if, for instance, we can imagine what I have in mind is a satellite which is a 2D a 2D object, so it has the advantage to be manufactured in 2D. And when it gets into space, it can become a 3D object. So it can be a cube and antenna shape. It can be a rover in the future, landing on the moon and then exploring the moon. So basically, we imagine a satellite which is a total transformer, you can imagine. So which reaches different stages at different time and operation time. I hope you enjoyed. Thank you. If you have any question, I'm happy to answer.